Hey everyone, welcome to the quick and visual guide to one of the most powerful sorting algorithms, quicksort. In this video, we won't write a single line of code. Instead, I'll walk you through how quicksort actually works by following step by step how this sorting algorithms is used and why is so popular. Whether you're preparing for an interview, learning algorithms for the first time, or you just want to finally understand how quicksort breaks down arrays and builds them back up, this video is for you. In this video, I will explain how quicksort works. No code, just examples and visualizations of the algorithm. We'll see how quicksort chooses pivots, how it splits arrays, and how it finally sorts everything step by step. Why quicksort? It's one of the fastest sorting algorithms for general use. Sorting isn't just a school topic, it's used everywhere. It's used on search engines, databases, AI systems, and even in financial markets. Sorting makes data faster to search and easier to process. That's why algorithms like quicksort are so important. It's used on search engines such as Google, etc. in programming languages. For example, we have quicksort, which is used as the default sorting algorithm for Java and Python. It has an average time complexity of O n logarithmic n, which makes it much faster than a simple sorting techniques like bubble sort. Why sorting is important? Sorting is essential for making a large amount of data more searchable and manageable. For example, we have a contact list and we want to sort for searching. For example, when we type Ron, then we have to make a searching list, but it would take too long without sorting. Or for example, if we filter emails by date, it would take too long if we didn't sort them. So it's not just a school topic, it has a real usage. For example, in search engines, to use sorting to rank results, databases use quicksort for efficient indexing and searching, operating systems use for scheduling algorithms. So quicksort is fundamental for high performance computing. And today we will analyze in this presentation how it works and how it's implemented in Java and how to optimize it. What is quicksort? Quicksort is a divide and conquer algorithm. It picks a pivot element, then rearranges the list so that everything smaller is on the left, everything is bigger on the right. Then it repeats the process on both sides. The process is simple. We have to select an element from the array as a reference. Then we partition array from the left and larger elements on the right. We recursively apply quicksort to the left and right parts. So when all parts are small enough, the array becomes sorted. How quicksort works? We have a given array of these elements 8, 3, 1, 9, 7, 2 and 6. We select a pivot Selecting the pivot element is crucial because it affects performance. The last element is often chosen because it has advantages. For example, it has a simple implementation. We simply use the last element on the list. Works well in random data. If the array is unsorted and random, the last element is as good as any other pivot choice. It has consistent code structure, and many textbooks and programming examples use this approach for clarity and consistency. It has easy implementation without extra swaps. When the pivot is the last element, it remains in place while partitioning happens, reducing swap complexity. Some of the issues with choosing last element as a pivot are worst case performance for sorted or nearly sorted arrays. If the array is already sorted or reverse sorted, the last element will be the largest or the smallest from the list. This results in an unbalanced partition. One side has many elements and the other has few. It leads to O(n) square complexity, which is the worst case. Also can cause poor performance on large datasets. On large datasets, unbalanced partitions increase recursion depth, which can slow execution. We might have alternative pivot selection strategies, such as first element, which is the low. We have a random pivot, and we have a median of 3 pivot, first, middle, and last. Selects the pivot as a median of low, middle, and array high position. It helps to prevent unbalanced partitions, reducing worst-case performance. It is used in high-performance sorting implementation like C++, STL's quick source. Now, in this case, we'll select the last elements. How the partition of the array works. We move smaller numbers to the left, smaller than 6. So the elements that are smaller than 6. Move the larger elements to the right, so the elements that are larger than 6. And the array would look like this, as you can see. This is our pivot element. The elements that are smaller than the pivot are moved on the left side. How it works? We have the given array of this example. Is 8 smaller than 6? Yes, move to the right. Is 3 smaller than 6? Move to the left. Same for 1. And 9 is bigger than 6, so it moves to the right. 7 is the same. And the 2 is smaller than 6, so it moves onto the left. So then we apply the quick sort recursively on the left and the right subarrays. What to do if the element is 6? We apply the smaller or equals to 6. So this will send 6, for example, to the left side. So for example, we have even a 6 here. Then we would have 3, 1, 2, 6. Why it doesn't matter? Because we have the 6 as pivot element, but the 6 is on the left side, the other 6 that we imagine that is in our list. Is this sorted? Yes, because we have, for example, when we do recursively the quick sort, when we apply, we have 1, 2, 3, 6, 6. They are equal, so we have them on random positions. So 6, 6, 6. They are bigger than 3, but lower than, for example, in this case, 7. Now, how does the Java code look like? We have the main method that we apply the same elements of our array list. We use the quick sort. We use array 0, array length -1. Now we see the code. In where we see the main method that has an array uses quicksort and prints the array. So we print the new array that will be 1, 2, 3, 6, 7, 8, 9. Sorry for this. As we thought, it's important to choose the pivot that is best for the algorithms, as if it's nearly sorted, we told that last element might cause problems, so they won't impact bad in performance. The initial unsorted array is this. The Java code to implement is this. We simply add integer array brackets, we use a variable name, and we use the elements that we fetched. Step 1 of this quicksort algorithm, choosing the pivot. We used the last element as our pivot, so we don't know if the list is sorted or not. In this case, we know it's not sorted or nearly sorted or reversely sorted, so we choose the last element. The process for this is by choosing array high. High means the last element, highest position. Partitioning around pivot is the second step. Partitioning works as follows. We compare each element with the pivot. Elements smaller than 6 move to the left. Elements greater than 6 move to the right. So the pivot is placed in the correct position. After partitioning, the array looks like this. Elements that are smaller than 6 and the elements that are greater than 6. This is the Java code that does the partitioning. The low element, high element, and the list of elements, the array of elements. We choose the pivot last element, which is length -1. So we had 9 elements. Used the length -1, which is 8. As we know in Java, arrays work with 0, 1, 2, 3, 4, 5, 6, 7, 8. The 8th element is number 6 in our list. So 1, 2, 3, 4, 5, 6, 7. In this case we have 7 elements. I'm sorry, we don't have 9. So we have 0, 1, 2, 3, 4, 5, 6. For us, the 6th element is the pivot. It is 7th element, but with the index 6. Now, we point for smaller elements. So we have low -1. We start from the low to the high position, and we increment +1. If the element is smaller than pivot, I moves ++. We use the swap method to swap smaller elements to the left. We set swap, this is a pivot, this is smaller elements, and this is greater elements than the pivot, which is 6. We swap elements to the left. First we have the list, the group, the array that had 3, which is the first element that gets swapped and goes to the left side. Then we have elements of the array 3, then 1, then 2, then we have elements that are greater than 6, which are 8, 9, 7. This is the second step after choosing the pivot. And this, if the element is smaller than pivot, we move to the left. So if it's not, then move to the right. Then we have the third step, recursive sorting. We use the left subarray, which is 3, 1, 2. Now we start by choosing pivot for our subarray. We have the array with 3, 1, 2. We choose again the last element, which is 2. What happens here? We recursively do the same thing. We choose the pivot 2. Now, we choose elements that are smaller than 2. It's 1, that moves to the left. And the elements that are greater than 2 is 3. And now it's correctly positioned. And as we check, it's sorted. The left part is now sorted. The Java code to do this is same one. Pivot index -1. What is pivot index -1? It's 0, 1, 2, but we have 3 elements. As its third element, we use pivot index, which is 2 minus 1. Before sorting the array, we left array 3, 1, 2. After sorting, it's 1, 2, 3. Now, doing the same on the right subarray, the elements that are greater than the pivot. Now we do the same. We select the last element as pivot of our right subarray. The first original subarray is 8, 9, 7. Selected 7 as a pivot. We added the quick sorting method. We moved the left elements. We moved the smaller elements on the left, and the right part we used the greater elements. So now, as you can see, the partitioning after sorting is 7, 8, 9. So it's already now sorted. Now, at this stage, we have sorted both left and right subarrays. We do the combining of the sorted partitioning to get the fully sorted array. 1, 2, 3 that were lower than 6, and 7, 8, 9 that were greater than the first pivot 6. We have these 2 pivots, 7 and 2. 7 didn't have any, or was it 7? No, the pivot, yes, the pivot was 7. Now it's interesting here. Let's turn back. We have the pivot 7, the left side and right side. Which is 8 smaller than 7? No. Then 8 on the right side. Is 9 bigger than 7? Yes, 9. So you have no left elements on the left subarray. Then we have the sorted elements 7, 8, 9. The code to print is print array, so it prints the sorted array. And the final sorted array after recursive quick sort is 1, 2, 3, 6, 7, 8, 9. How the recursion tree is represented. We had the first initial array with 7 elements. We had the pivot 6. Then we had the subarray, left subarray with 3, 1, 2. 6 is now placed in the right position. The right elements were elements that are greater than 6, which was 8, 9, 7. Then we had the left and right elements of pivot 2. So we had 1, 2, 3 that was sorted. Simply 2 is the pivot element. Elements that are greater than 2 move to the right side, and on the left side we have elements that are smaller than the pivot. The same applies to the right subarray. We have pivot 7. Then on the right side we have both elements as they are both greater than the pivot 7. How does quick sort Java code look like? The function to perform quicksort is simple. We had the array that we wanted to sort. The low is the 0 position, as we told that arrays start from the 0 position, and the high position is the length minus 1. We found the pivot position, recursively sorted elements before and after partitioning, and then we finally, this is the function to partition the array. As you can see, we have found the pivot position, then we partition array on the with pointing the smaller elements that are elements on the left, place correct position of the pivot, then function to swap two elements. What does this function do? So we have 3, 1, 2. Let's take just 3 elements. We did swap elements every time. For example, we want to swap from this array, we want to swap 2 with 3. We assign a temporary variable. We use the element we want to first swap. For example, we have 2, which is in position 2. Or in fact, we want to swap into third position, the third element, which is 0, position 0, 1, 2. Now, the temporary position takes, no, the 0 position in fact, takes, in this case 0, takes the value of the element that we want to swap it with, which is the element on the index 2, which means on the 0 position we have 2. Now the array looks like that: 2, 1, 2. How do we turn down the 3 element into the second position? We simply assign the array at 2 the variable that we stored as temporary. So now the temporary variable that stored the array at 0, which was 3, now it's gotten back into the position that we wanted to sort. We do this as an example, even why we don't need this, because when we choose the pivot on 2, 1, 3, for example, we choose 3 as pivot, and move smaller elements on the left and greater elements on the right. At this case we don't have greater elements, so we move 2, 1, and the position of third is okay, and we just swap the position of the two elements if the pivot, if the element is smaller than the other. For example, in this case, we do the 0 position and 1 position. We want to swap these elements. We store this into a temporary variable. Then we swap this into this position. Then we have 1, 1. And then we move the temporary variable into the position of the second element. And then we get this swapped and sorted. This is the main function to test the quicksort. First we have the unsorted array. We print the original array, then we perform the quicksort, and then we printed the sorted array. The quicksort has multiple complexities. It has O(n) log n when the pivot divides array evenly. So we had, in our example, 7 elements. We have the pivot on the center, and we have 3 elements on the left, 3 on the right. It's the best case. Worst case is when the smallest or the largest element is always picked as a pivot. As we told in the beginning, if we have a sorted array and we try the quicksort, then it's the worst case, as we cannot find a good complexity when we do the choosing the smallest or largest elements as a pivot. We have the space complexity O(n) log n, O log n, because of the recursion. We have quick comparison of quicksort versus merge sort. Merge sort is used often. It has always a O(n) log n, but uses extra memory, while quicksort is faster but has a worst case. The time complexity of quicksort and merge sort is same, but worst case complexity is better for merge sort. But why we use quicksort? Because it doesn't use extra memory. It's faster in most cases, while merge sort is stable and predictable. Where it's used quicksort? Quicksort is used in Python's sort method and also Java's array sort method, while merge sort is used in libraries. The advantages and disadvantages of quicksort. It's fast, in place, and widely used. As we told, its disadvantage is its worst case scenario, if the pivot selection is poor. Thank you very much. This was a video just to show you why and how quicksort works. It works, as we told, on every day in search engines such as Google's search engine, where results are sorted by relevance, or on Amazon, where products are sorted by price or ratings. Sorting is the engine behind those operations. So sorting isn't just a school topic, as we mentioned, it's used everywhere in the real world.